We finally found it. Grab it and get out of here. And watch out for that bed of nails.
I see the bed, Professor Joules.
Finally, after this long adventure, the apple is mine.
Wait, Professor, I think it's booby trap.
Oh, you're right. The apple is perfectly balanced with that mess over there. If I remove the apple, the balance will tip and trigger a booby trap.
I see that, Professor. I'm not dumb.
Well, your grades in my classes show otherwise.
Good, low pass.
You're lucky I continue to keep you as my graduate student. Whoever set this trap was a physicist.
Why is that?
Why, it's staring us right in the face. T for torque. You know, torque. It states that the farther the distance a force is away from the fulcrum, that's this point here where the teeter-totter teeters, so to speak, the more force it will exert. So even if we place the same mass on both sides, the mass which is farther away will go down more due to a greater distance and greater torque. Here, I shall demonstrate with this silver weight.
How can you afford a silver weight?
Ep-Sallah, I'm a physics professor. Of course I can afford. It appears this is lead. I forgot my funding I cut last year. Watch this, Ep-Sallah. I can drop the mass on this side, and it'll hardly budge. But even if I gently place the mass on this side, the whole thing will start tipping over. Now, I must calculate the mass, which I will switch the apple with. Which I will do by multiplying times the volume of an apple. Now, I'm going to approximate that apple as a sphere. Which means that the volume of the apple is equal to 4/3 times pi times the radius cubed. Now, because this is just a rough calculation, I'm going to go ahead and round pi to 3.
You can't round pi to 3. You're not an engineer.
Now, hold the balance for me while I switch the weights.
I'll hold it. There's no way this is going to work. It's definitely going to fall.
It's not going to fall. Who thinks it's going to fall?
That's me up here.
Oh, no. You told me to count to 3. All right. Here we go.
Professor,
Oh, fell!
I knew this was going to happen. This is why you never round pi.
Oh.
Professor, argue.
Caused by gravity, because your body is spread across a lot of nails, instead of the points touching your body, is distributing enough pressure to push you into the nails.
That's great, Professor, but I almost died because of you and your rounding.
Math. Why does it always have to be math? I hate math.
Darn experimentalists. I knew I should have gone into theory. Give me all your minutes.
Here. Blasted! My math skills have failed me again. No matter. We must return this apple to the UC Davis archives.
Wait, UC Davis has archives? Is that where my homework is? It's been a month.
Well, I might have lost that, but I promise it's TA's fault. My nemesis, Nilé Bohr-oq. I'll never forgive you for cheating off me in graduate school.
I shall once again take your work and publish it as my own. Maybe this will finally win me the Nobel Prize I so deserve. Now, give me the apple.
Never!
You know, Dr. Joules, we do similar work. I just have perhaps a different method. Goodbye now, Dr. Joules. May we never meet again.
Professor Joules, are you okay?
Yes, I'm fine, but blasted, I lost the apple. No matter, we must return to UC Davis and let them know he lost. Looks like I'm going to have to apply for more research funding again.
So another year of unpaid research?
We'll paid an experience. So, as you can see here, the energy required to move one electron through 1 volt of potential difference is equal to 1.6 times 10 to the negative 19 joules. Any questions? Yes, in the back.
I'm sorry, isn't that just 1 electron volt?
Excuse me.
He's a plant.
I am Professor Joules, not Professor Electron Bolt. Get out!
Jesus, Professor, do you mind if we ask a question real fast?
Oh, Dean Schrodey. It's nice to see you. Class dismissed. And remember to graduate next week. How can I help you?
Hi, this is Special Agent Bill Nye. From the National Science Foundation. He's here to talk to us about a hands-on research proposal?
Thank you, Dean Schrodey. As I'm sure you're well aware, it's the mission of the National Science Foundation to promote and protect the advancement of science in the United States. After all, science rules. However, it has come to our attention that a certain Professor Nilé Bohr-oq is in pursuit of the Bohr-oq at CERN, Switzerland.
Well, the lost Quark, that's just theory. Weakness? Why, of course, the standard model of particle physics classifies all of the fundamental particles and forces in the universe. See, here we have the force carriers, Bohr gauge bosons, and the Higgs boson. These are responsible for things like electromagnetism and the nuclear forces. Matter is made of fermions up here. There are 6 leptons and 6 quarks, which are named up, down, strange, charm, top, and bottom. But some physicists believe in the existence of a 4th generation quark as a contender for dark matter.
It says here that mysterious evidence of this 4th type of quark was discovered at CERN, but then promptly lost? Some of you might be familiar with CERN from the work that UC Davis does there. Anyway. We're worried that Bohr-oq is going to try and find this missing quark and use it to get the Nobel Prize. And since this is a National Science Foundation proposal, national, we'd rather keep that honor to U.S. physicists.
You can tell why it's integral that you find the quark first. We want you to go to Switzerland and beat Bohr-oq to the discovery. We believe he's after the lost lenses now. It's the key to finding the quark. We also believe your former advisor, Professor Bayron Brookehavenwood, is in possession of those.
Well, why should I go looking for this particle?
You're a partial physicist. This is quite literally your job.
Well, I'm woefully unequipped for field work.
Why you'll be needing this.
What do I need this for?
Don't you know how a whip works?
Well, of course. When a whip is thrown, it creates a small loop which travels down the length of the whip. As the loop moves, it gets smaller, which causes it to increase in velocity due to the conservation of energy. Eventually, the loop will reach the speed of sound. When it does so, it creates a small vacuum in the air. This vacuum makes a sonic boom, which is the cracking sound commonly associated with the whip. Here, we'll demonstrate.
So you see, you are prepared for field work. And you're also ready to begin your journey to Switzerland.
Oh, one water, please. Hello, Bayron. Nice to see you, too.
Indiana Joules. I always knew you'd come walking through my door someday. What do you want? My father isn't here. He's retired.
I'm looking for something your father used to have. I remember seeing it when I was his graduate student. It's the lens of Snell. Medallion-shaped thing with the crystal in the middle. I believe it can point me to the lost Quark.
Quark? You're after the Nobel Prize, aren't you? You haven't changed a bit since grad school. That's why you were the worst lab partner. I failed that class because of you. Now I'm here, listening to the physicists from CERN complain about their latest failed experiments.
Reduce Planck's constant?
H-bar. Look, my father gave me the lens to protect it from people like you.
Listen, if I know about the lens, Bohr-oq does too. He'll be coming after you, and he won't take quite as kindly to being doused in water.
That's not the point. The point is every time...
And Miss Bayron Brookehavenwood. I believe you have something of mine, the lens.
You'll have to take it by force.
Then prepare to have your mass accelerated.
Give me the lens, or you'll be hit by the zaps.
Never!
Your funeral.
The magnets stop the axe.
But how? This axe looks like it's made out of aluminum, and aluminum isn't magnetic.
No, but aluminum is a conductor. And when a conductor passes through a magnetic field, all of those free electrons inside can start flowing. This generates an induced electric field, or an induced electric current, also known as an eddy current. When the eddy current passes through these two magnets right here, it generates its own magnetic field, which generates a force pointing this direction, which slows it down. However, if we were to use a different material, let's say wood for example, which is not a conductor, we wouldn't expect such a thing to occur. See, wood doesn't have all those free electrons, so when it passes through the magnetic field between here, no current will be induced, and therefore no force will occur.
What? Hang on, let me see.
If we let it go... See, you must have skipped your electricity and magnetism class.
Luckily for me, I didn't pass that class.
Indy! Help!
They took her. Now they have Bayron and they're this close to finding the Quark. Hey, what's this? She was always one step ahead of me. Now that I have the lens, I can beat Bohr-oq's team to finding the Quark and winning the Nobel Prize. There's no time to waste.
Linear accelerators, circular accelerators, boosters, ion rings. What a mess, Dr. Joules. How are we ever going to figure out where to find the Quark?
Well, if we're going to figure out where to find it anywhere, it's going to be in the lobby of the LHC, the Large Hadron Collider. So just keep looking around. Bill said that the lens of Snell will guide the way. We know that the Quark has to be somewhere in the LHC, but we don't know exactly where to look.
Professor, is this Hayes' real Nobel Prize?
Unfortunately not, Ep-Sallah, but we need to focus on the matter at hand, quarks.
Right, because quarks make up matter. Anyway, this looks really familiar.
Oh, you're right. It looks exactly like a lens minus the large piece of glass in the middle. Oh, looks like there's some writing on it. Focus on what's ahead to see the light at the end. Young 700 nm? What on earth is that supposed to mean?
Lens. You taught us that lenses are used to focus light. Maybe it can show us something?
Oh, brilliant, Ep-Sallah! Ah, and I have just the thing. Here's a flashlight. Okay, and I'm going to turn it on. Well, that didn't do anything. The light just dispersed through. We're not going to be able to find anything with this.
Wait a second. Young is the physicist who taught us that light is actually a wave.
Oh, yes! Yes, of course! Light is a wave. And young 700 nm, young 700 nanometers. That gives us a wavelength of light. And if I recall correctly, 700 nanometers should be a red light. And I have just the thing. I knew my pocket lasers would come in handy.
Do you just carry around pocket lasers?
Well, you never know when you're going to need to point at something from a distance. Here, watch this. Oh, look, the laser's pointing at those prisms. Someone must have set them up to direct the light to point at the location of the quark. See, normal light is a combination of multiple wavelengths, which are all diffracted at different angles. But lasers are a single wavelength. Thus, prisms simply alter the direction of the beam. And look, there. That's what was detected. The compact muon solenoid. 14,000 tons, 15 meters in diameter, and 21 meters long. Filled to the brim with electromagnetic calorimeters, hadronic calorimeters, and a nice steel yoke that confines magnetic field 100,000 times out of the Earth. If the lost quark were to be anywhere, it'd be here.
So, like an egg?
Huh?
Well, you said it's got a yolk.
Your degree is a yoke. Come on, let's go find this quark.
What about Baryon?
Oh yeah, her too. Let's go.
Hey, watch where you're stepping.
Ah, sorry. And look, the lost quark. So it does exist.
Baryon too.
Here, quick, get me out before they come back. Oh, thank you. I was tied up for so long.
We found it.
Well, is it in there?
Well, it could be.
Could be.
Particle?
The particle in the box.
Could it not be?
It could not be.
Well, why don't we just check?
No.
How do we know if it's in there or not?
Well, there's an equation.
I thought you hated math.
Well, until we check if the particle is in the box, it both is and is not in the box.
What's the point of particle physics if you don't even know what particle you have or if you have it?
No, not point. It's a wave.
What?
Never mind.
All particles are waves?
Well, technically yes, but only at very small scale.
That makes no sense.
Wait, this was on our homework last month. Is that the box?
Enough. You're both
You mean wave?
no. Subatomic particles are subject to the laws of quantum mechanics. They're not like dust where they can just be in one corner of the box or another. You see, subatomic particles act like waves. We can't know where they are, only where they might be. So the only way to know if we've detected the lost quark is to look at the trail produced by the collider, which only exists for a fraction of a second.
So it's not in the box.
What?
Well, if the quark has been missing for weeks and it only exists for a fraction of a second, how can it still be in the box?
You're right. Good point.
Wait. Whoa.
What is it?
Joules! Thank you for doing all the heavy lifting for me. Now, get this.
No, I just got out of this.
Silence!
How did you find us?
Your companion wasn't very forthcoming, but we knew you'd make your way here eventually. Not even you can resist the temptation of discovery. It was a simple matter of luring you here. And now that you've done all the hard work, it is I who will enjoy the privilege of being first author.
Andy, what's going on?
Making history, Miss Brookehaven. You see, there are many different ways to detect particles. One of the earliest types is a cloud chamber, much like this one here. This appears to be a dry ice or frozen carbon dioxide. Inside the chamber is ethanol vapor, which, when a charged particle, much like the lost quark, passes through it, it will ionize its surroundings, showing up as a faint vapor trail for all visible for all to see.
But to detect the lost quark, you're going to turn the big ring. You hope to recreate the lost quark here and now. But Bohr-oq, you can't.
I'm sorry, Dr. Joules. I can't hear you. I'm too busy booking my tickets to Stockholm.
Here. Take this lead. Put it in front of your eyes.
Hurry!
It's really deep in my bag.
What about me?
There, see it? The faint trails, just like little wisps. We can use it to find out if this is truly the lost Quark. Come, let us look closer. It's beautiful. It's... Why does it feel like my face is melting?
It looked okay to me.
Thinking, Dr. Joules, using the lead to protect our bodies from the harmful radiation.
And the ropes just fell away. How convenient.
Professor, I think there's a problem.
Is that tungsten?
Oh, that sneaky little...
Hey! This is a family show. We don't curse here. Joules, why is there tungsten in the cloud chamber?
Oh, I think Bohr-oq was trying to fake results. He was skeptical he would be able to reproduce the lost Quark, so he put a source in the cloud chamber. This source produces alpha particles. That's what the chamber picked up, not the Quark.
So, we didn't find the Quark?
No, but don't give up. Science is full of failed experiments. The important thing is we stop the dishonest physicists from publishing fraudulent work. Now we must continue our work at UC Davis. Let's go report back to Agent 9.
You've done UC Davis a great service, and I trust you'll find your settlement satisfactory.
There.
Run any research program of your desires, all in silver bars.
Well, Bill, while all this silver is nice, what I think I would want to see most is the lost Quark.
I've told you already, Dr. Joules. We've moved the analysis team conducting that research to the bottom of the UC Davis physics building. They're now looking for the short-lived particles that are a signature of the decay of the lost Quark.
Well, what sort of quarks?
Top quarks.
That's strange, but I think it can help.
You're charming, Dr. Joules. Make sure to call you up.
I'm down.
Until next time.